So it turns out that the method that we've established for solving a second-order differential equation works for any homogeneous second-order differential equation. Remember, homogeneous meaning the right-hand side, there's no function of t. Everything is just in terms of y or its derivatives. So it turns out that this works regardless of what kind of eigenvalues that we have. So let's kind of use that trick and say, if you know this is our second order differential equation, then that translates into a characteristic polynomial that would look like this. S squared plus 4s plus 13 equals 0. And if that's the case, then it's a little bit complicated because this is not something that factors nice and neat. But we can still solve it. We can solve it for s and say s is going to be equal to, using our quadratic formula, -4 plus or minus the square root of 4 squared, so 16, minus 4 times -4, 4 times 1 times 13, so -4 times 13. And in the denominator, because our leading coefficient is just 1, it's just 2. So with a little bit of effort, we find out that 16 minus this guy in here becomes total of -36. So we have s is equal to -4 plus or minus root -36 all over 2, which is, after a little bit of effort, equal to -2 plus or minus 3i. So that means that our s value that would make our guess, our lucky guess of e to the st true, actually is a complex number. But that's okay. The method still works. And that means that we can write our general solution, right? If you have two values for s, then that means that you have a general solution that looks like this. Y of t equals k1 times e to the, pick the first one of these, -2 plus 3i times t. Remember, that's the whole eigenvalue times t, plus my second solution, k2 times e to the -2 minus 3i times t. Now you might be thinking, hey, do we really need both of these things? Well, hang on. We're going to follow the method and say, keep both of our particular solutions in there, throw constants in front of them, and that gives me my general solution. Now, I could stop there, but of course, it's not really legitimate to stop there because I'm dealing with imaginary numbers. So we're going to have to expand these things a little bit. And so I'm going to start by kind of factoring out e to the t, or e to the -2t from both of those. And what I'm going to do is I'm going to kind of back off and say, look, I know that there's a general solution, k1 and k2 times those particular solutions, but I'm just going to imagine, what would it look like? What would it look like if we were just dealing with the particular solutions? So for right now, I'm going to ignore k1 and k2. Now, the reason I'm ignoring them is because they're going to pop back in later on as constants. We're going to pick up constants along the way, but we can ignore k1 and k2 as constants, right? So they're just along for the ride. Right, so we don't have to do anything fancy with them. And so my y of t is going to be equal to, I'm going to factor out e to the -2t, because that's a common factor for both of these two terms. And then what I have left inside is k1 times e to the 3it, and then the other one is k2 to the, or times e to the -3it. Right? So both of these I'm going to expand, and I'm going to use a little color coding here to be able to kind of follow along with what's going on. So let me see if I can get some different colors that'll show up. Okay, so that's going to be my green, so I'll hold on to that. And, oh, just for giggles, I'll make this blue. It's a little bit darker. So on the next line down, I'm going to expand these using Euler's formula. So I'm going to add a little note off to the side. Expand using Euler. And when I do that, I have e to the minus 2t times k1 times this whole thing, the underlined green thing, using Euler's expansion is going to be cosine of 3t plus I times sine of 3t. Right? All of that is equivalent to the green up above, right? Plus the second term, k2 times, using Euler's expansion, cosine of negative 3t plus I times sine of negative 3t. Now, if you're being kind of savvy at sitting there and you say, hey, cosine of a negative, that means something. You're right. Hold on. So I've just expanded it. Now, one thing that you probably recognize, or you should recognize from your trig class or your pre-calc class, is that when we start taking cosines and sines of negatives, they have particular value. So I'm just going to expand all this out, multiply it through, and see what we get. So I'll have k1 times cosine of 3t plus I times k1, not ki, k1 times sine of 3t. I should have put the I in front of the sine, and it doesn't matter. Cosine of negative 3t is exactly the same as cosine of 3t. That's a trig definition here. So this really is just the same thing as cosine of 3t, right? And if you're not convinced, it's like saying cosine of negative 90 degrees is the same thing as cosine of positive 90 degrees. You get the same result either way. But it doesn't work that way with sine. With sine, the sine of a negative angle is the negative of the sine of the positive angle. So this is the same thing as minus k2 times I sine 3t. Right. So all I've done right now is multiplied it out, and I used a little bit of trig identities over here to write the equivalents. And so underneath, let's see if I can identify the fact that I have two terms that are completely real and two terms that are completely imaginary, right? Because they have the I in front of them. So I'm going to group those together inside my brackets here. So I'm going to scoot this up so I can keep showing on the screen. E to the minus 2t. Inside the brackets, I'm going to group my real terms together. So it's going to be k1 plus k2 times cosine of 3t. And then my imaginary terms I'm also going to group together. Notice there's a subtraction there. So there's going to be an I times a constant, k1. So this is going to be plus I k1 minus I k2. I'm grouping them together like that on purpose, times sine of 3t. And just to kind of be consistent here, these two terms right here are my real terms, and these two terms are my imaginary terms, and they group together. Now you might look at it and go, ugh, God, it's a mess, but what does it mean? Well, let's kind of play this out and say we've got e to the negative 2t times the sum of two constants. Well, the sum of two constants is just itself a constant. So I'm going to call that C1 for constant. And over here, I know you're looking at it and you're like, but there's an imaginary number. But that imaginary number can get kind of sucked in. It's just a constant. It doesn't have to be a real number. We'll call it a constant number 2. So after all is said and done, I really do have constant 1 times e to the negative 2t cosine 3t. That's that first multiplied through term. Plus constant 2 times e to the minus 2t times sine of 3t. Now take a look at what we came up with. This is the general solution for the position equation, if you want to think of it that way. This isn't a matrix equation. This is a parametric equation. This is a scalar equation. Now, you might think, okay, well, that's great, but if I want to know the velocity equation, well, remember, we didn't start off knowing that this was a harmonic oscillator. It may be, it may not be. The only thing that I can say for sure is, after all is said and done, this is the y of t, the general form of the y of t, that solves that differential equation. Right? And so by using the trick of Euler expansion, I find out that there really is no imaginary term that just gets kind of pulled together as a constant sitting in front of a sine of 3t. So at this point, this is the position equation, if you want to think of it that way, that solves that second order differential equation. So I'm going to write underneath here, if our original second order differential equation represented a harmonic oscillator, then this y of t, is the position, is the oscillator's position equation. It's the solution, right? If you wanted to know what the velocity equation is, all you'd have to do is take the derivative. So we could know v of t by finding y prime of t. Notice we'd have to do a little bit of calculus because each one of these is a product rule situation if you're going to take the derivative. So it's a little bit of Calc 1, right? It's not super complicated, but it's a little bit of calculus. If we solve this thing by converting it into a matrix equation first, so that we're solving a system of two linear differential equations, then we don't have to do any calculus, but it's a whole lot more algebra, right? So it's this kind of question, this balancing act. Are you going to do more calculus and less algebra, or are you going to do more algebra and less calculus? Either way, you can get to a solution. But please, please pay attention to the idea that we didn't start off saying this was a harmonic oscillator. It doesn't have to be. It might be. And if it is, then we can get to this part down here and say if that's the position equation, we can find y prime to get the velocity equation. You can get the exact same result using the eigenvalue eigenvector method. It's just more tedious. So if you have the shortcut for a second order differential equation, by all means use it. Right? So the last little bit of 3.6 is actually some notes that I want you to take a look at. And there's a link. You can get to the link by, well, you already have this as a handout, but you can also get to the link by clicking on this thing in the PDF of the notes. And the PDF of the notes, let me see if I can pull it up here. I thought I had it up. Did I close it accidentally? Oh, I thought I did. Hold on, let me open this thing up. So this is what it looks like, the quote-unquote bonus handout. It's basically me going through the process of saying, for a harmonic oscillator, what does undamped look like mathematically? What does damped look like mathematically? And what are the different types of damping? There's the overdamped case, there's the critically damped case, and then there's the underdamped case. And so what I want you to do is look through this, and in all three cases you'll be able to get a sense of what's going on. The overdamped, the underdamped, and the critically damped case are the three possibilities where you have damping. If you have an undamped harmonic oscillator, it's really boring. It's kind of what we expect. So that ends the chapter 3 notes. There's one last page that kind of pulls together all the different situations that we may have run into, all the different possible linear systems that we've run into. What happens when you have eigenvalues that are both negative, but they're different? Well, then you have a sink, and one of them is going to be more influential than the other. What happens when you have a saddle. Well, that means you have one positive and one negative. So some of this stuff is going to look really familiar. These first three, these are really basically 3.2 and 3.3. So sections 3.2 and 3.3. The next couple that we run into right here are actually section 3.4. When you have spiral source, spiral sink, or center, where it's not spiraling in or out, that means you must have an imaginary eigenvalue, or two imaginary eigenvalues. And then actually all of the remainders, all of these are special cases. All of these are special cases that get dealt with in section 3.5. And specifically, these guys right here are the ones where we use the ballad, because you have a repeated eigenvector. Right? So this page is really just kind of a sum up of chapter 3, all the stuff that we've kind of put into place for chapter 3. Now that we know we can solve any system of linear equations regardless of the type of eigenvalue that they spit out. If it's a real eigenvalue, if it's a repeated real eigenvalue, or if it's an imaginary eigenvalue, we know how to solve all of those. So that gets us to the end of chapter 3. I want you to take a look at the notes from those quote-unquote bonus notes for overdamped, underdamped, and critically damped. And then you can tackle the last problem set 12. Okay, I'll see you for chapter 4.